Welcome to Lecture 5, Section 2.2, Sequences and Sets. We are using the text Advanced Calculus by Patrick M. Fitzpatrick. This is Dr. Gilbert, Eyabi. Section 2.2, Sequences and Sets. Let's start by recalling that a subset S of real numbers is said to be bounded if it is bounded above and also bounded below. i.e., S is said to be bounded if I can find a real number m such that the absolute value of x is less than or equal to m for every element x in the set S. So what we are saying here is that negative m is less than or equal to x, which is less than or equal to m. So negative m is a lower bound and m is an upper bound. It's bounded above, bounded below, so the set is said to be bounded. We would now extend this concept to sequences. Subsection 2.2.1 definition. A sequence an is said to be bounded provided that there is a number m such that the absolute value of an is less than or equal to m for every index n, i.e., the sequence an is bounded if I can find a real number m such that the absolute value of an is less than or equal to that real number for every natural number n. Let's go ahead and look at a few examples. Example 1. Define the sequence Sn by Sn equals summation k from 0 to n, 1 divided by 3 to the k. Now you can quickly write 1 divided by 3 to the k as 1/3 raised to the power k. And we end up with summation k from 0 to n, 1/3 to the k to be our definition for the sequence Sn. And a quick recall from what we did back in chapter 1, the geometric sum formula, one of the tools for analysis, this equals 1 minus 1/3 raised to the power n plus 1 divided by 1 minus 1/3. And simple algebra would lead us to 3 over 2 minus 1 over 2 times 3 to the n. 2 is a positive number. N is a natural number, so it's positive. 3 is positive, so 1 divided by 2 times 3 to the n is positive, and I'm subtracting a positive number from 3 divided by 2. No matter how small this number is, the difference will be less than or equal to 3 divided by 2. So we can say that Sn is less than or equal to 3 over 2. Put a pause right there. Now let's go back and look at the definition of Sn. Summation k from 0 to n, 1 divided by 3 to the k. The lowest value of k is 0. And if that happens, we end up with 1 divided by 3 to the 0, which is 1. So we see that Sn is a sum of positive terms. Therefore, Sn is greater than or equal to 0 for every natural number n. Sn is less than or equal to 3 divided by 2. Sn is greater than or equal to 0, which of course is greater than or equal to negative 3 over 2. So we can say that the absolute value of Sn is less than or equal to 3 over 2 for every natural number n. And if we set our m to be 3 divided by 2, which is a real number, we can conclude that Sn is a bounded sequence. Are all sequences bounded? No. Example 2. We call this sequence a harmonic sequence, and we shall observe in section 2.3 that this sequence is unbounded. So far, we know what it means for a sequence to be convergent, and we also know what it means for a sequence to be bounded. So we are ready for our first proof in section 2.2. Subsection 2.2.2 theorem. Every convergent sequence is bounded. Interesting. So if a sequence converges to a point A, that sequence is bounded. Let's go ahead and look at the proof. Proof. Let an be a sequence that converges to the real number A. Required to prove. I want to prove that the sequence an is bounded, i.e., I want to find a real number m such that the absolute value of an is less than or equal to m for every natural number n. Let epsilon equal 1. Then epsilon is greater than 0. By the epsilon n definition, following the convergence of an to a, we can find a natural number n, uppercase N, such that the absolute value of an minus a is less than 1 for every natural number n greater than or equal to the uppercase N. Call that inequality 1. Also observe that an equals an minus a plus a, and if I take the absolute value of an, that gives me the absolute value of an minus a plus a, and applying one of the tools for analysis that we learned back in chapter 1, known as the triangle inequality, that is less than or equal to the absolute value of an minus a plus the absolute value of a, and call that inequality 2. Look at the inequality 1. The absolute value of an minus a is less than 1, and that holds for every natural number n greater than or equal to uppercase N. Bring that into inequality 2, this quantity right here, we end up with the absolute value of an is less than or equal to 1 plus the absolute value of a, and that holds for every integer n greater than or equal to uppercase N. We would have gone ahead and set our m to be 1 plus absolute value of a, and then we would say that the absolute value of an is less than or equal to m, and we are done. But not so fast. This inequality only holds for every natural number n greater than or equal to uppercase N. So what about a1, a2, a3, right up to a uppercase N minus 1? Are we sure that this inequality holds? Well, to settle that, we define m to be the maximum of 1 plus absolute value of a, which is what we have on the right hand side of this inequality, comma, the absolute value of a1, the absolute value of a2, the absolute value of an minus 1. So whichever one of these is the maximum will do the job. If that is the case, then we can conclude with confidence that the absolute value of an would be less than or equal to m for every natural number n. Not just for greater than or equal to uppercase N, but for every natural number n. And that concludes the definition of boundedness, and so we can conclude that the sequence an is bounded. So every convergent sequence is bounded. Now, before we get to see this later in this course, start thinking about this. Would every bounded sequence be convergent? Can we add something to the boundedness of a sequence to make it convergent if we cannot conclude that every bounded sequence is convergent? Well, when we get to section 2.3, we would address that question. Now, let's go on to something that we saw back in chapter 1. The density or the denseness of a subset S of the set of real numbers. Recall that a subset of the set of real numbers S is said to be dense in R, the set of real numbers, if every interval a, b, where a is less than b, contains an element of S, i.e., if I pick an open interval AB, A less than B, no matter how small this open interval is, I can always find an element X that is from S. If that happens, we say that S is dense in the set of real numbers. What we want to do now is to provide a characterization of denseness in terms of convergent sequences. Before we get there, let's look at an important definition. Subsection 2.2.3 definition. Let S be a subset of the set of real numbers. The sequence xn is in S provided that for each index n, xn belongs to S, i.e., if S is a subset of the set of real numbers, then we say that the sequence xn is in S if and only if every term of that sequence is in S. Let's look at an example. Define the sequence xn by xn equals 1 over n. Then we see that the sequence is a subset of the half-closed interval 0, 1 open at 0 and closed at 1. And that is so because for every natural number n, 1 over n is an element of the half-closed interval 0, 1 open at 0 closed at 1. In this case, our set S is the half-closed interval 0, 1. Now we are ready for that great characterization of denseness. And that would be proposition 2.2.4. A subset S of the set of real numbers is said to be dense in R if and only if for every real number x there is a sequence in S that converges to that real number. i.e., a set S is dense in R if and only if whenever I pick a real number x, I can always find a sequence xn in S that converges to x. So I have to prove both ways. Proof, forward direction. Suppose S is dense in R. Let x be a real number chosen arbitrarily. We have to find a sequence Sn in S such that Sn converges to x. Now this is a very systematic proof, so let's go ahead and follow it. Let n be a natural number. By the denseness of S in the set of real numbers R, there exists a member of S in the open interval x plus 1 over n. Again, it doesn't matter how small this interval is, because S is dense in R, I can always find an element in S that sits in this interval. So let's call that element Sn, i.e., Sn is in the open interval x plus 1 over n. That simply means x is less than Sn, which is less than x plus 1 over n, and if I subtract x from all sides, I end up with 0 less than Sn minus x less than 1 over n. We have done this before. That means the absolute value of Sn minus x is less than 1 over n. Observe that negative 1 over n is less than 0, which is less than Sn minus x, which is less than 1 over n. So we can correctly say that the absolute value of Sn minus x is less than 1 over n. Wait a minute. What have we just done? We have defined a sequence Sn that has the property that the absolute value of Sn minus x is less than 1 over n for every natural number n. Call that inequality 1. That's very important to us. Now, so as to be able to apply a lemma that we have seen before, why don't we rewrite inequality 1 as absolute value of Sn minus x less than 1 times the absolute value of 1 over n minus 0. Again, that holds for every natural number n. This one here is our real number c. 1 over n converges to 0. We proved that back in section 2.1. This is our constant c. So by the comparison lemma, we can conclude that the sequence Sn converges to x. So we picked an x from the set of real numbers. We have found a sequence in S that converges to x, and that proves the forward direction. So if a subset S of the set of real numbers is dense in R, then we have shown that every number x is the limit of a sequence in S. So let's go ahead and look at the reverse direction. Conversely, suppose S has the property that every real number is the limit of a sequence in S. So if I pick any number arbitrarily x, I can always find a sequence in S that converges to that number. I am required to prove that S is dense in the set of real numbers R. But what does that mean? It means if I am given an open interval AB, A and B are real numbers, A is less than B, I must find an element X in S that sits in that open interval AB. So, let the open interval AB be given. A and B real numbers, A less than B. Define the element X as X equals A plus B over 2. We do not know whether X is in S or not, but we do know that X is going to be the midpoint of the open interval AB. So it is clear that X is an element in the open interval AB. It is actually its midpoint. But if X is the midpoint of the open interval AB, it means X is a real number. By our hypothesis, there exists a sequence in S called the sequence Sn such that Sn converges to X. That is what the reverse direction says. We are assuming that every number is the limit of a sequence in S. In particular, the number X, A plus B over 2, would be the limit of a sequence in S, and let's call the sequence Sn. Now, Sn converges to X. That brings us to the epsilon n definition of convergence. So why don't we set our epsilon to be b minus a divided by 2? Observe that if b is greater than a, then b minus a divided by 2 would be greater than 0. So by the epsilon n definition of convergence, Sn converges to X means there exists an uppercase natural number n such that the absolute value of Sn minus X is less than epsilon for every natural number n greater than or equal to uppercase n. Again, what does this mean? We've done this several times. That means Sn is an element of the open interval X minus epsilon, X plus epsilon for every natural number n greater than or equal to uppercase n. If you have forgotten how we got here, this inequality means negative epsilon is less than Sn minus X, which is less than epsilon. Add X on all sides and we end up with this. X minus epsilon would be A plus B divided by 2 minus B minus A divided by 2, and that gives us A. X plus epsilon, A plus B divided by 2 plus B minus A divided by 2, which gives us B. So what we are actually saying is Sn is an element of the open interval AB, and that happens for every natural number n greater than or equal to uppercase n. That means from uppercase n, all our Sn's are in the open interval AB. So in particular, S index uppercase n is an element that belongs to S and also belongs to the open interval AB. We picked our open interval AB arbitrarily. A and B are real numbers, A less than B, and we have found an element S index uppercase n from S that is in that interval. Therefore, we can conclude that the set S is dense in R, and we have proved the reverse direction and hence the proposition. Beautiful. The next theorem is a consequence of proposition 2.2.4. Theorem 2.2.5, sequential density or sequential denseness of the rationals. Every number is the limit of a sequence of rational numbers. I.e., if I pick a real number x, I can always find a sequence of rational numbers that converges to x. As a matter of fact, it also holds for the set of irrational numbers. And the proof is straightforward. We proved back in chapter 1 that a set of rational numbers is dense in R. And therefore, by proposition 2.2.4, every number x in R is the limit of a sequence of rational numbers. End of proof. And that will be the same proof for the sequential density of the irrationals. Here is another exciting lemma. Lemma 2.2.6. Suppose Dn converges to the number D, and every term in the sequence is non-negative, i.e. Dn is greater than or equal to 0 for every natural number n, then we can conclude that the limit of the sequence D is also non-negative. In other words, a sequence whose terms are all non-negative cannot converge to a negative number. Interesting. And it needs a proof. Let's go ahead and look at the proof. Proof. We proceed by contradiction. Suppose Dn is a sequence that converges to D, and all the terms of the sequence are non-negative. Now assume on the contrary that the limit of the sequence D is a negative number. If D is negative, then negative D would be positive. So negative D divided by 2 would be positive. Set our epsilon to be negative D divided by 2, which is a positive number. Then since Dn converges to D, by the epsilon n definition of convergence, I can always find an uppercase natural number n such that the absolute value of Dn minus D is less than epsilon for every natural number n greater than or equal to uppercase n. But as we have done before, this simply means negative epsilon is less than or equal to Dn minus D less than or equal to epsilon. Add D on all sides, and we end up with D minus epsilon less than or equal to Dn less than or equal to D plus epsilon. But what is epsilon? Negative D over 2. So what will be D minus epsilon? It will be 3D divided by 2. What is D plus epsilon? It will be D divided by 2. So for every natural number n greater than or equal to uppercase n, all the terms of the sequence Dn would be between 3D over 2 and D over 2. But D over 2 is negative. In other words, from uppercase n right up to infinity, all the terms of the sequence Dn are negative because they are all in this interval which consists entirely of negative numbers. But that is a contradiction because our hypothesis says Dn converges to D and all the terms of Dn are non-negative. And now we have ended up with so many terms, infinitely many as a matter of fact, being negative. This contradiction arises because of the assumption that our limit D was negative. Therefore, D is greater than or equal to 0. Or we say D is non-negative. End of proof, and we're done. Subsection 2.2.7 theorem. I actually love this theorem. Let Cn be a sequence in the closed interval AB. I just used that word closed very loosely. And you probably already know by now that this interval is called a closed interval. Well, I'm going to take you to another level of the definition of a closed interval before we get done with this section. If Cn converges to the real number C, then we conclude that C also belongs to the closed interval AB, i.e. if the sequence Cn is in the closed interval AB, that means closed at A and closed at B, and Cn converges to C, then C also has to be an element in this closed interval. Let's go ahead and look at the proof. Then we would define what it means for a subset of the set of real numbers to be closed sequentially. Proof. Let Cn be a sequence in the closed interval AB, and suppose Cn converges to the number C, we are required to prove that C is an element of the closed interval AB, i.e. A is less than or equal to C, which is less than or equal to B. We're going to break this up into two. We will show that A is less than or equal to C, and C is less than or equal to B. We would start with the second inequality. C is less than or equal to B. Now, by linearity, the limit as n approaches infinity of B minus Cn is just B minus C because Cn converges to C. Pause right there. We'll come back to that. Now, the sequence Cn is in AB means that for every natural number n, A is less than or equal to Cn, which is less than or equal to B. Call this inequality here 1 and call this other inequality 2. Let's start with the first inequality. Cn less than or equal to b implies that b minus Cn is greater than or equal to 0 for every natural number n. But we just saw up here that the limit as n approaches infinity of b minus Cn is b minus c. So b minus Cn is going to converge to b minus c. But b minus Cn is greater than or equal to 0 for every natural number n. By the lemma we just saw above, lemma 2.2.6, the limit of this sequence, which is b minus c, would also be greater than or equal to 0. In other words, b is greater than or equal to c, or we say c is less than or equal to b, and that is the first inequality we have here. Similarly, we prove the second inequality and we're done. So similarly, from this inequality 2, we can say that c minus a is greater than or equal to 0, or a is less than or equal to c. And 1 and 2 would lead us to both inequalities, and we can conclude that a is less than or equal to c, less than or equal to b, or that c is an element of the closed interval AB, and we're done. I would leave you to write out the details of this second case. Just do it exactly as we did the first case, Cn less than or equal to b. Now let's go ahead and provide what I call the sequential definition of closedness for a subset S of real numbers. We say that a subset S of real numbers R is said to be closed provided that if there is a sequence an in S that converges to a number A, then A also belongs to S. So a subset of the set of real numbers is closed provided that if I can find a sequence in S that converges to a limit, the limit must also be in S. That does not say that every sequence in S converges, but if one converges, it must converge to a point in S. An converges to A. Dn converges, it converges to D. Any sequence in S that converges must converge to a point in S. Interesting. So the closed interval above, which we saw in Theorem 2.2.7, is closed because whenever there is a sequence Cn in that interval and the sequence converges to C, C also belongs to that interval. So that is what I call the sequential definition of closedness. So if I ask you to state the sequential definition of closeness, I expect you to tell me about the convergence of sequences in S to limit points in S. Example, the closed interval 0, 1. Closed at 0, closed at 1 is closed. Why? Well, directly from Theorem 2.2.7. Number 2, the set of rational numbers and the set of irrational numbers are not closed. Why? Because of denseness. Example, let's pick the number 2. This is a rational number. It is a real number. By the denseness of the set of irrational numbers, I can always find an irrational sequence xn such that xn converges to 2. Remember the sequential characterization of denseness? Xn is an irrational sequence. It converges to a rational number. So QC is not closed. Similarly, Q is not closed, again because it is dense in R. What about this interval? S equals the half closed interval 0, 1, open at 0, closed at 1. If I ask you to prove that this interval is not closed, I expect you to find a sequence in this interval that converges to a point outside the interval, okay? So throughout this course, if I ask you at any point to prove that a set is not closed, the idea is to generate a sequence that comfortably sits in that set but converges outside the set. So in this case, let's look at the sequence 1 over n. In fact, 1 over n is known as l'enfant chéri, one of our beloved children. Okay, we would use that example in so many cases, just like the interval 0, 1. So the sequence 1 over n is a sequence in S that have closed interval 0, 1, and as we saw back in section 2.1, 1 over n converges to 0, which is not an element in S. Therefore, S is not closed. What if I gave you S to be the half-closed interval -3, 10? Can you generate a sequence for me in that interval that converges outside the interval? Go ahead and play with that. That brings us to the end of lecture 5 and section 2.2, sequences and sets. Our next step would be lecture 6, which would handle section 2.3, the monotone convergence theorem. Recall that we have not yet answered the question, if a sequence is bounded, is it convergent? If that does not hold in general, are there some conditions that we can add to a bounded sequence to make it convergent? We shall answer that question in section 2.3, lecture 5. Thank you and God bless you.